Well, let's say we're given the following setup. Let me make sure you can see my notes decent here. 21A, today is the 11th of February. Here's the setup. A rock is thrown upward. From the top of a 64-foot building. With an initial, let's pass that. With an initial velocity of 48 feet per second. The rock's height or position at time t is given by h of t equal to negative 16t squared plus 48t plus 64. And before going on, I'll just point out this is a pretty standard formula. More generally, this is equal to the acceleration due to gravity divided by 2. Right, because the acceleration due to gravity is negative 32 feet per second, and negative 32 divided by 2 is negative 16. So it's your gravity term divided by 2, your initial velocity, and your initial height. So in general, if someone gives you those pieces of information, they're asking you to find the position function or the height function. This is always how it's going to work. If it's in, at least if it's in feet per second, right? If it's in meters, it's a different coefficient, but that's the idea. So then we like to ask some question, like, what is the rock's height after 1 second or 2 seconds? What's a relatively straightforward question to answer? We're just going to plug in those values. So the height after 1 second is going to be negative 16. Now, when you're plugging in 1, do we really need to write 1 squared and 48 times 1? And 6? No, we just write, we know what's going to happen. I mean, negative 16 times 1 squared plus 48 times 1 plus 64, which is going to be 96. 96 what? 96 feet. After 2 seconds, well, plugging in 2, we're going to get negative 16 times 2 squared plus 48 times 2 plus 64, which I didn't check my math ahead of time, so let's see here. I will point out that negative 16 times 4 and is 64. It's negative 64, and so is that. So those cancel out, and we end up getting 96 feet. It's like it didn't even move, but it did, obviously. Like, right, the rock was going, well, maybe not obviously. So, right, the rock was going upwards. It hit a height of 96 feet. It probably continued going upwards, turned around, and then on the way back down, also hit a height of 96 feet. Like that. So there's time equal to 1 second. There's time equal to 2 seconds. It wouldn't be a very interesting question, but I'm going to ask it anyways. What's the average velocity between 1 second and 2 seconds? Well, here's the not exciting answer. The average velocity from time equals 1 to time equals 2 is going to be, well, it's the change in distance or the displacement, which is 0 feet, right? Because it came back to exactly where it was. So from where we started at time equals 1, we haven't moved at all. It's our position at time 2 minus our position at time 1 divided by the change in time. That's going to be 96 minus 96 over 1, which is 0. So the average velocity is not that interesting. Or maybe it is interesting because, right, what we're saying here is that even though we know that the rock definitely traveled, right? It went up and then came back down. The average speed or the average velocity over that time is 0 feet per second. Let's look at the more interesting question. What's the instantaneous velocity, or the instantaneous rate of change at each of those moments? So we're talking about instantaneous rate of change. Always a fun word to spell. Instantaneous velocity at time equals 1. That's just a way of using more words to say what's the derivative of the position function. How is the position changing at this one moment in time? You can just set that down. So we're going to find the derivative of position. So position, again, I'll write it down here, is negative 16t squared plus 48t plus 64. And we're going to find the derivative as a function of time, which is going to be negative 32t plus 48, which is exactly the velocity at time t, which definitely would matches up with what we said about the initial velocity being 48. Because if you plug in 0 for time, you will get 0 plus 48, which is 48 feet per second as our initial velocity. And then if you think about what gravity is doing, the acceleration due to gravity is negative 32 feet per second, or people say feet per second squared. I think feet per second actually evokes a better idea of what's happening. So every second that time passes, we're going to slow down by 32 feet per second. So after 1 second, instead of traveling upwards at a velocity of 48 feet per second, we're going to subtract off 32 and now be going only 16 feet per second, which is exactly what you get when you plug in 1, right? V of 1 is going to be negative 32 times 1 plus 48, which is 16. So after 1 second, we've slowed down quite a bit from a blistering pace of 48 feet per second to a much, much slower 16 feet per second. And then if we look at what's happening at the velocity after 2 seconds, well, if we plug in 2, we're going to get negative 32 times 2 plus 48, which is negative 64 plus 48, which is negative 16 feet per second. What does that even mean? Well, the rock was going up, and we were imagining the upward direction as the positive velocity direction. And now that the velocity is negative, we know it means the rock is traveling in the downward direction. Both of these moments in time, the rock has the same speed. The speed going up is 16 feet per second. The speed going down is also 16 feet per second. The velocity is the speed paired with the direction. It's like a vector. So the velocity at 1 second is positive 16 feet per second. At 2 seconds is negative 16 feet per second. Cool. What else do we like to ask here? I have a couple of things in mind. Oh, yeah. So what's the maximum height? Have we even gotten, yeah, sure, yeah, why not? What's the maximum height of the rock? Well, to answer that question, we need to know when it reaches the maximum height, which you might be able to guess based on the things I've already said. It's not, we're going to show it anyway, but it wouldn't be wrong to think, well, we were at a height of 96 after 1 second. We went up and we came back down to the same height after 2 seconds. It's probably the middle of those two numbers, and it is. The way we're going to find it is by saying, well, it's going to be where the derivative, aka the slope of the tangent line, is going to be 0, because we're going from a positive velocity on the way up, and then 0 at the top, and then a negative velocity on the way down. So we're going to take our velocity equation, which is negative 32t plus 48, and set that equal to 0. Or in other words, we're setting the derivative equal to 0. And I know we haven't really talked about this much, but as we move forward, we'll talk about how to find where a function has a maximum or a minimum. We find those critical points by setting the derivative of the function equal to 0. There's more to it than just that, but that's the start. Solving for t here, we get negative 32t equal to negative 48. So t is going to equal 48 divided by 32, which reduces to 3/2, which is 1.5. Exactly halfway between 1 and 2, as we suspected it might be. We're not done though. The question didn't say, when does the rock reach its maximum height? The question asks, what is the maximum height? So we have to take that critical point where we reach the maximum height and then plug that back into the height equation. So we're going to say, okay, the height at, in my opinion, it's easier to plug in a fraction versus a decimal. I know what 3/2 squared is. It's 9/4. 1.5 squared is a little more work in my brain. So I'm going to plug in a fraction to make it easier. It's going to be -16 times 3/2 squared plus 48 times 3/2 plus 64. And solving this is -16 times 9/4. 48 times 3/2 is 24 times 3 plus 64. -16 times 9/4, I can cancel a 4 and say -4 times 9 is -36 plus 72 plus 64, which adds up to some number, 108. Sorry, I can't say that. Apologies. So that's our maximum height, 108 feet at a time of 3/2 seconds or 1.5 seconds. Interesting. Okay, one more question. So I would say for objects thrown in the air specifically, the kind of typical classical questions are, what's the maximum height and how fast is it going when it hits the ground? So that's the other question we'll ask here is, how fast is it going when it hits the ground? And no, it is not 0 feet per second. That's after it hits the ground, right? Right as it hit, right? If you hit the ground at 0 feet per second, falling wouldn't be a problem, right? You'd be totally fine, but it's clearly a problem. So, right, let's see. So first, just like before, to figure out how fast or what something is at a particular moment, we have to find the moment. So we have to find when the rock hits the ground. That's going to be when the height of the rock is 0. So we're going to set the height of the rock, which was -16 t squared plus 48 t plus 64 equal to 0. Looking pretty quadratic to me. I'd much rather not use the quadratic equation if I didn't have to, though. And this problem's definitely been written with care. Each of these numbers is a multiple of 16. So we can definitely factor out a -16. So I'm going to say we have -16 times t squared minus 3t minus 4. And so then if we factor this more, it does factor as t minus 4 times t plus 1. So it's either going to hit the ground after 4 seconds or 1 second before we threw it, which doesn't really make sense. But it kind of does make sense, actually. If you look back at the picture I actually do kind of poorly now that I think about it, because, right, my picture actually started at the wrong spot, kind of. Good job, James. I don't like my picture anymore. I'm going to draw a picture again. So the picture that we kind of have, which I will fully admit drawing kind of wrong from before, is more like this, actually. Right, where here's our 1 second, here's our 2 seconds, here's 3 seconds, and here's 4 seconds. And then if you went back to 0 seconds, if you went back in time to -1 seconds, the ball would be hitting the ground as well. Sorry. Also, as a reminder, if I'm off the page, off the screen, let me know, because I'm always like, what's going on? It's hard to kind of see down here. So then we're going to plug that into which equation? The velocity, right? Because we're trying to answer the question, how fast are we going? So great. Velocity at time t is -32 times t plus 48. So we plug in 4. And the v of 4 is going to be -32 times 4 plus 48, which is -128 plus 48, which is -80 feet per second. So if they ask just how fast, you don't really need to include the negative. So we could say that our speed is 80 feet per second. That's how fast we're going when we hit the ground. we happen to be going in the downward direction, but it doesn't really matter. All right. I've done my due diligence, talked about that. Sure. Let's move. We can always revisit that topic, but it's usually not everything. Sorry, I'm missing something here. One moment. Where'd you go? So let's talk about. Let's start with an example. Let's say that we want to find the derivative of x to the fourth plus 1, let's say cubed. Sure, let's say cubed. We didn't do this already, did we? I don't think so. No. Okay. I'm sorry. I feel like I did this example with someone recently, and so it's always hard to remember what exactly. All right, so we're gonna do this two ways. The first way, we're just gonna multiply it out. So I'll remind you from our Pascal's triangle stuff that if you have something plus something cubed, like a plus b cubed, that's just the third row of Pascal's triangle. It's gonna be your 1, 3, 3, 1. That's gonna be a cubed plus 3a squared b plus 3ab squared plus b cubed. So here, we're going to be finding the derivative of x to the fourth cubed plus 3 times x to the fourth squared times 1 plus 3 times x to the fourth plus 1 cubed. I guess I could have written 1 squared there and 1 cubed here. Simplifying that one more step before we actually differentiate, we're going to get x to the 12th plus 3 times x to the 8th plus 3 times x to the 4th plus 1. And now we'll take the derivative just using the power. So we're going to get 12x to the 11th plus 24x to the 7th plus 12x cubed. And normally I would just leave the answer as is. But I want to simplify this a little bit to help us see something important. So I'm going to factor out a 12x cubed. I'm left with an x to the 8th, a 2x to the 4th, and a 1. And I will point out that this actually factors as x to the 4th plus 1 quantity squared. We've got 12x cubed x to the 4th plus 1 squared. Okay. Here's the way we're actually going to do it, because you don't want to do this every time, especially with the power. Like 3 is a pretty tame power, but what if the power was 30, right? There's no way you're multiplying out x to the 4th plus 1 to the, and none of us are multiplying out x to the 4th plus 1 to the 30th power, right? It's just too much. So here's the more general idea. And this is the language I like to use, and I would encourage you all to use. I have some stuff to the third power. What's the derivative of x cubed? Right, you all know it's 3x squared. So replace x with some stuff. The derivative of x cubed is 3x squared. The derivative of some stuff cubed is 3 times your stuff squared. But there's something else, right? We don't have the same answers over here. We're off by a multiple of 4x cubed. In other words, we're off by the derivative of that. So here's the sentence I would say. It's a lot, but I'm going to say it anyway. The derivative of x cubed is 3x squared. The derivative of some stuff cubed is 3 times your stuff squared, but then you have to multiply by the derivative of the stuff. If you ever say the magic word stuff, it means at the end of the process, you have to multiply by what? The what? The derivative of the stuff. The word derivative is super important there. So at the end of this chain rule process, you're always multiplying by the derivative of the inside function or the inside stuff. That's kind of the whole thing, really. Like it can be more complicated than that, but at the end of the day, that's the big picture idea of the chain rule, is that you're always differentiating the outside function, leaving the inside pieces alone, and then after all of that, multiplying by the derivative of the inside piece. Kind of the whole story. But let's do more examples because, well, it's good to do more examples. And also we'll kind of derive this rule as well. Kind of fun to derive. Well, let's just look at one more example. So let's say I wanted to find the derivative of, sure, we'll come back to this one as well. So I want to find the derivative of sine of 2x. Okay. Well, we know the derivative of sine of x is cosine of x. So the derivative of sine of some stuff is going to be cosine of that stuff multiplied by the derivative of the stuff, which in this case is just 2. And this example also is important. We'll see in a little bit here. But I do want to show you kind of why this is true. Now, I will admit, this first example does kind of show it, right? Because when we did it the long way, we exactly got 3 times x to the 4th plus 1 cubed times 4x cubed. Sorry, squared. That's the square. That's the square. Right? These are the same. That there and that there. Just took a different path to get there. But let's talk about how they actually are the same no matter what. So just for a moment here, let's say we want to find the derivative of any old function raised to the nth power, where we're imagining n is a positive integer, but it actually be anything. So remember how I talked about the triple product rule and the quadruple product rule a little bit, kind of, maybe? Maybe not. Okay, let me remind you about the triple product rule. So let me remind you about the product rule. We know that the derivative of f times g is f prime times g plus f times g prime. And more broadly, if you had a product of 3 things, how many pieces am I going to get?
3.
3. And each piece is going to have how many derivatives? And the rest not derivatives. And each derivative gets to show up exactly 1 time. So you're going to have like f prime times g times h plus f times g prime times h plus f times g times h prime. And you can go on and on, right? This idea holds for any number of things multiplied together, whether it's 3 things or 7 things. For 7 things, it'd be 7 pieces, and you'd have each derivative showing up once, multiplied by the other 6 not derivatives. And that even is true if you have n things multiplied together. So here's what we've got. If I want to find the derivative of something to the nth power, well, I'm really thinking of the derivative of, I'm going to write f instead of f of x. I have f times f times f times f n times. Okay, when I do this n tuple product rule, how many pieces am I going to get? N. And each piece is going to have 1 derivative and the other n minus 1 not derivatives. So we're going to have, okay, it's going to be f prime times a bunch of f's plus then it's going to be f times f prime times a bunch of f's all the way till the very last one, which is going to be, squeezing in here, f times f times f times all the way to f prime. Let's put some parentheses around these so it looks a little less ugly. But each of those things I'm adding together has 1 f prime and n minus 1 f's. Well, great. I could rewrite this then as f to the power of n minus 1 times f prime plus another f to the power of n minus 1 times f prime plus all the way to the very last term being another f to the power of n minus 1 times f prime. How many pieces did we say we had? n. So if I'm adding the same thing together n times, it's like if I had 5 plus 5 plus 5 n times, it'd be 5 times n. This is going to be that thing times n. Sorry, that thing, just one of them times n. So it's going to be n times your function to the n minus 1 power times the derivative of your function. Or written slightly more nicely, write it up here, the derivative of some function raised to the nth power is going to be n times that function to the n minus 1. Oh, that looks like the power rule. Times the derivative of the inside. Chain rule. I should be more specific here. This is specifically the power rule version of the chain rule. It's not the most general chain rule version, but it does elicit that chain rule idea that we are differentiating the outer function being raised to the nth power. We're leaving the insides alone. And then after we do all that, we multiply by the derivative of the inside. You're probably going to hear me say that a lot of times, but it's really the very important idea of how the chain rule works. So why do I feel like all my examples have disappeared on me? Sorry, I feel like my notes somehow I missed a page or something of the notes I usually like to bring with me. That's fine, just slightly annoying. It's okay. I can think of lots of fun functions to differentiate. Like a fire alarm. I'm sorry.
Like worksheet.
Sure. Sure.
I don't know how to solve.
What's the question? Is it from the web work?
No, it's like a worksheet that he made
Okay, what kind of topic is it on?
chain rule and horizontal and vertical tangent.
Okay, go ahead, hit me. You can bring it up or you can say it either way. Number one here. So this is giving us this function. Find the x coordinate. Okay, let me write this down. We'll get there in a minute. Third. Okay. Yeah.
Thank you.
So let's do a few more examples using the chain rule because I do think it's good practice. So let's say, for example, we were given a function that was 3 sine x plus x cubed to the 5th power. So not a big deal, right? It's just, as I'm seeing it, it's some stuff to the 5th power. I'm really a fan of the word stuff. It might be my favorite math word. So some stuff to the 5th, the derivative is going to be 5 times that stuff. We have to leave that stuff alone to the 4th power. So that stuff is 3 sine of x plus x cubed. And then after that, we're going to multiply by the derivative of the inside stuff, which is going to be 3 cosine of x plus 3x squared. And if I write it like that, it's wrong. Because I have to multiply my derivative of my outside by the entire derivative of the inside. And if I don't have a parentheses around this, it looks like I'm just multiplying by 3 cosine of x. So we have to have parentheses like that. And then we're safe. Why don't you all try this one? Find the derivative of, I'm going to give you a tangent for tangent of x plus x to the 7th power, all raised to the negative 12th. we should be getting, there's some stuff to a power comes down, we get -12 times all of that to what's my new power? -13. Right, the powers get more negative or less positive. Then we're gonna have to multiply by the derivative of the inside stuff. Okay, the 4 hangs out, the derivative tangent of x is secant squared of x, and then the derivative of x to the 7th is 7x to the 6th. So definitely the power rule versus the chain rule, not too terrible. You've got a bunch of stuff to some power. You do the power rule on the outside, leave the inside alone, multiply by the derivative of the inside. But the chain rule works for any composition of functions. The general way of writing this, there's a few maybe ways. Probably the preferred way is to say, if you're taking the derivative of f of g of x, well, like I've said already a few times, we take the derivative of the outside stuff, which in this case is the f function. We leave the insides alone, which is our g of x. And then we multiply by, on the outside, the derivative of the insides, g prime of x. And because it's sometimes useful, another way of writing this, which is using, how do I want to write this? Sorry, there's like a few different ways people like to write this. Another way to write this is to say that, yeah, I'll go this way. Let's say that dy dx is equal to dy du times du dx. To me, this is much less, it doesn't feel like the chain rule. But you're like, where is all this great? So let's actually kind of backfill this just so you can kind of see what we mean here. So what we're really thinking here is that y is a function of u is a function of x. And so if I want to take the derivative of that, well, check it out. If I took the derivative just using the chain rule I've got over there, it's like I have y prime of u of x multiplied by u prime of x. But that is exactly what we've written over here. This dy du is our y prime of u. We're just kind of ignoring the fact that there's an x inside that u. And this du dx is exactly your u prime of x. And this dy dx is exactly your derivative of your original function. I don't love this notation as much, but it has its uses, especially when we start talking about related rates. It becomes very convenient to write things like this because what you might think here, and you're not exactly right to maybe think it, but you're not wrong either, is that it kind of looks like we could cancel out what? The du parts, and then dy over dx, oh, that's dy over dx. So cancellation wise, like it looks like how you would think it should look if you were just trying to write something down. So it's very convenient to be like, oh, well, I don't know what dy dx is exactly, but I know I can write it as dy over d something, and then the same d something over dx, and then kind of make a convenient change. Again, especially useful when we talk about related rates, which are not that far off. Okay, so my example for this, right, the chain rule, one of your teachers kind of showed you the proof of it, but it's not exact, like there's a little more to it than just what they showed you. But there's a good example I really like to show you, which we already found the derivative of. So let's graph something. So we're going to graph y equal to sine of 2x. We're going to graph sine of x as well, just for the sake of it. So let's graph both sine of x and sine of 2x. Sure, let's use red. This red pen's almost dead too. Gotta re-up my pens here. So let's see. We know that sine of x has a period of 2 pi. Break it up into 4 quarters. Amplitude of 1. And in red, I'll graph sine of just x first. So 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's -1. And at 2 pi, it's back to 0. And I do really feel like this pen. There we go. That is a much better red pen. There's my sine of x function. So can anyone tell me how sine of 2x differs, or what changes? Not the amplitude. The amplitude would change if we had a 2 out in front. The period changes. And the way I like to kind of think about it is for y equal to sine of x, to get one full period, the angle has to go from 0 all the way around to what? 360, or in radians, 2 pi. So here we need x to go from 0 to 2 pi. Okay, well, for sine of 2x, we need the same thing to be true for the angle. But for sine of 2x, the angle isn't x, the angle is 2x. So we need our angle still to go all the way from 0 to 2 pi to get one full period. But then if we think about what x has to do, if we divide everything by 2 to isolate x, 0 divided by 2 is 0, 2x divided by 2 is x, and 2 pi divided by 2 is pi. Oh, our period is now from 0 to pi. If x goes from 0 to pi, 2 times x will go from 0 to 2 pi, and we'll get one full period in half the space. So our new sine of 2x function looks like we've just kind of squished the sine of x function over by a factor of 2. And if you wanted to draw another period, you could. Another way to think about it is whatever this number is here, that's how many full periods you get in 0 to 2 pi. So for sine of 2x, you would get 2 full periods. For sine of 3x, you would get 3 full periods. It's another way of imagining what's going on. So there's my one full period sine. Now let's graph the derivatives. Like how we did before. So as we know, the derivative of sine of x is cosine of x, but let's graph it anyway. Because graphing the derivative, okay, well, the slope of the tangent line here is going to be positive 1. The slope of the tangent line here is going to be 0. Slope of the tangent line there at pi is going to be negative 1. And then at 3 pi over 2, it's going to be 0. And at 2 pi, it's going to be back to 1. So not surprisingly, there's the graph of the derivative of sine of x, which is cosine of x. This pen also, this pen looks like it has plenty of ink in it. Well, fine. Sorry about that. Not the day for red pens. Okay, so now we're going to graph the derivative of our sine of 2x. And I want to point out that at the origin, the slope of the tangent line to sine of x is positive 1. And for sine of 2x, it certainly looks like it is steeper. Right? That blue graph definitely has a steeper slope than the red graph, meaning the derivative has a larger value. And although it's hard to tell exactly what it is, I will just tell you flat out, it is 2. So we're starting off at a value of a derivative of being 2. And then right here at pi over 4, we're getting a derivative of 0. And then over here at pi over 2, we're getting a derivative of negative 2. And then over here at 3 pi over 4, 3/4 of the way through our period, we're getting a derivative of 0 again. And finally, back after one full period at pi, we're getting a slope of positive 2 again. So here's our new graph. Okay, so let me ask everybody. Now, let me ask you a terrible question, because technically either answer is correct. But does this look like a sine graph or a cosine graph? It looks like a typical cosine graph. You could just technically say it looks like a sine graph. You shifted left or right, but we're not shifting left or right. It's a cosine graph. Okay, the amplitude of this cosine graph is 2, and the period is still pi. So it looks like this graph is going to be 2 times cosine of 2x. The 2x gives us a period of pi. And the 2 there gives you your amplitude. But hey, look, that's exactly the derivative of sine of some stuff times the derivative of the stuff, right? That's your cosine of your stuff multiplied by the derivative of the inside stuff. So there's an example graphically of why, oh yeah, the chain rule really seems like it should work. We don't just, right? Our derivative certainly isn't just cosine of 2x, right? The slopes aren't positive and negative 1. The slopes are larger. So the chain rule really is a valid thing. And definitely, I would say from here on out, you should approach every function you're differentiating with a, is this more complicated than just a function of x? Is the inside function something that is more complicated? Okay. So let's look at some more examples. Let's say we want to find, for example, the derivative of, how complicated do you want to get? Oh, we'll start with this way. Sure. Tangent of x cubed plus secant of x. So now our outermost function is tangent. Tangent of some stuff. Our derivative of tangent, I should be more specific. The derivative of tangent of x is secant squared of x. The derivative of the tangent of some stuff is going to be secant squared of that stuff. And then we have to multiply by the derivative of all that stuff. 3x squared plus secant x tangent x. Sure. Let's do the following. Question.
We don't have to do product rule and then change.
So I want to ask a question to everybody. Does this function have a product? Are there any things that are multiplied together here?
Oh, no, it's a tangent. Oh.
Right. So I actually want to say stuff is probably my second favorite word in math. My first favorite word is the word of, because of is probably the most important word in mathematics you can say. I know people like to say just tangent or even just tangent x, but I would encourage all of you to take the extra split second to say the word of, because it actually really, really helps inform you about the functional nature of what's going on. Oh yeah, this is tangent of x cubed plus secant x versus tangent of x times x cubed plus secant of x. This is a whole different animal. And the fact that we said, oh, it's tangent of x times something else versus tangent of that stuff really makes a big difference. Here, we definitely would need to use the product rule. In fact, let's go ahead and use the product rule. Derivative of tangent of x is secant squared of x. Multiply by, you leave the other stuff alone. X cubed plus secant of x. Plus, then we switch it up. We leave tangent alone. Sorry, tangent of x. Follow my own advice here. Multiply by the derivative of the other thing, which is going to be 3x squared plus secant of x times tangent of x. Especially for secant of x, tangent of x, I've seen many people over the years say it's secant tangent of x and like forget the x in the middle there, and that is not a thing at all. You definitely need secant of x times tangent of x. Let's look at some more examples though. Oh yeah, I know what I want to do. So as a reminder, we've talked about how to take derivatives of x to a power or all of the trig functions, or we also have e to the x. We haven't really talked about natural log of x yet, even though I did mention it briefly at the end of our big derivative list. But we definitely could take the derivative of something like e to the x to the fourth plus cotangent of x. And I feel like this one of all of them, people kind of get thrown because unfortunately, because of the way we say this, the word of actually doesn't end up in there, right? You don't say e to the of, right? It's e to the power. Oh, I guess there's an up there. E to the power of x to the fourth plus cotangent of x. So the thing I'm thinking of is that my original function is e to the x. And the derivative of e to the x is e to the x. The derivative of e to the stuff, oh, I said the magic word, the derivative of e to the stuff is going to be e to the stuff multiplied by the derivative of that stuff. So it's going to be e to the x to the fourth plus cotangent of x multiplied by the derivative of x to the fourth plus cotangent of x, which is going to be 4x cubed. I'm not going to write plus negative cosecant squared of x. I'm going to write minus cosecant squared of x. Yeah, let's make it a little trickier. Because although certainly the chain rules can be applied here, you can apply the chain rule multiple times. So basically, if you have a function of a function of a function, if you have multiple compositions going on or multiple, I think one of your teachers called them layers, which I think is a good word. You just kind of keep working your way from the inside out. So let's look at another example. Example as always is interesting, sure. So let's say we want to find, we're given that the function f of x is equal to, sure, let's go with cosine to the sixth of e to the x plus x to the fifth minus 3. Sure, gross. Okay. So there's our function. And this one is always written in a way that I find terrible. Because the way it's written, it's not, in my opinion, immediately obvious what is the outermost function. What is the last thing that's happening to x? But if you rewrite it, I think it is more obvious. So whenever you have specifically a trig function to a power written in this abbreviated notation, I think it is always worth your while to rewrite this as cosine of whatever, e to the x plus x to the fifth minus 3, all of that raised to the sixth power. Because now it's more obvious that, oh, being raised to the sixth power is the outermost last thing that's happening. So when we start differentiating using the chain rule, we're going to say, oh, we have some stuff to the sixth power. We'll contrast that with a different example in a minute. So we're going to start taking the derivative here. Do I have enough room? Yeah, probably. So I have some stuff to the sixth power. My derivative is going to be 6 multiplied by that stuff. The fifth power. But now we have to multiply by the derivative of the inside stuff, and the inside stuff is more complicated than just something we can directly differentiate. The derivative of cosine of some new stuff is going to require the chain rule again. So the derivative of cosine of this new stuff is going to be, well, I know the derivative of cosine of x is negative sine of x. So the derivative of cosine of some stuff is going to be negative sine of that stuff, which is going to be e to the x plus x to the fifth minus 3. And then we have to multiply by the derivative of the stuff inside the negative sine function. So we have to multiply by the derivative of e to the x plus x to the fifth minus 3, which is going to be the derivative of e to the x is e to the x, the derivative of x to the fifth is 5x to the fourth, and the derivative of negative 3 is 0. So I didn't say the word stuff, I'm done. There is no derivative of the stuff I have to multiply by. Kind of gross. Kind of. I mean, there's grosser things though. You can always make a problem worse. Oh, yeah, it's true. Okay, so you can compare that with something like g of x equal to, let's say, sure, sine of e to the x plus 7x squared minus 4x, all raised to the sixth power. And now the trig function is the outermost function that's happening first, or last, I should say, really. So on the outside, we have a sine of some stuff, so then we're going to differentiate that first. So now our derivative is going to be, okay, g prime of x is going to be, the derivative of sine of some stuff is going to be cosine of all that stuff. Might not have enough room here. Cosine of e to the x plus 7x squared minus 4x to the sixth power. And then we're going to differentiate the inside, which we already know how to handle, right? We know how to handle something raised to the sixth power. Its derivative is going to be 6 times that stuff to the fifth times the derivative of that newer stuff. So we're going to get 6 times all of e to the x plus 7x squared minus 4x to the fifth power, but then we have to multiply by the derivative of the inside of that. And the derivative of e to the x plus 7x squared minus 4x is going to be e to the x plus 14x minus. Come on, pen. Yeah. For lack of a better kind of way of saying it, that's pretty much the gist of the chain. Yes, it can be grosser. Yes, the product rule, the quotient rule can also show up. So actually, sure. So actually, we should do a couple more examples with the product rule and or a quotient rule in there. Like, for example, if someone asked you, ooh, yeah, I'll do that, to find the derivative of the square root of 2x cubed plus 5 over 7x minus 9. And either you should rewrite it or at least think of it as the inside stuff raised to the 1/2 power. Right? Because square root's like, but 1/2 power is easy to do. So if we start we start differentiating here, our inside stuff raised to the 1/2 power, the derivative is going to be 1/2 times our inside stuff, the negative 1/2 power. But then we have to multiply by the derivative of the inside stuff. Sometimes when you're doing this, and you're like, I don't want to do that right this moment, you can take a break mentally and just say, okay, cool. In the next step, I know I have to multiply by the derivative of the inside stuff and just write that instead. To me, it feels like a waste of space, but sometimes you're just like, I don't want to do that derivative right now. Let me give myself some mental space to think about what's next. So then we can't just stop there, though. We still have to take that derivative using the quotient rule. So we're going to get 1/2 times all this stuff, 2x cubed plus 5 over 7x minus 9 to the negative 1/2 power times the derivative of this using the quotient rule. All right, it's the bottom times the derivative of the top, which is 6x squared, minus the top, 2x cubed plus 5, times the derivative of the bottom, which is 7, all divided by the denominator squared. And if there ever was a time to not simplify this, this would be the time. Unless asked to, right? But you should not simplify this unless someone is asking you to simplify it. And that's it. Kind of gross. Why don't you all try doing this one? I want you to find the derivative of, sure, let's make it not the worst thing you've ever achieved. Sure, let's do tangent of e to the x times x to the 5th. Yeah, I like that. Try finding that derivative. That. And before you leave today, I'm going to put this handed over here. I have a derivative worksheet along with not solutions, but answers on the back. So if you're looking for more practice here, so I'll be like, go ahead and do this kind of thing. Grab one of these, and if you have time, you can go home. So for this one, I've got tangent of some stuff. I know the derivative of tangent of x is secant squared of x. The tangent of this stuff is going to be secant squared of that stuff. But then we have to multiply by the derivative of the inside. I'm going to write it out kind of the long way. So derivative of the inside stuff. And now in the next step, I'll actually do that part. And you can skip that, right? You don't have to do this intermediate step that I'm doing. Just sometimes it's convenient or comfortable to do so. So I've got secant squared of e to the x times x to the 5th, which I probably normally would write as x to the 5th times e to the x, but I didn't. times, okay, product rule over here. The derivative of e to the x is e to the x. Leave x to the fifth alone. Add, switch, leave e to the x alone. Multiply by the derivative of x to the fifth, which is 5x to the fourth. And that's your gross final answer. Okay. So let's go ahead and answer that question that was asked over here about finding the following. So this is from, I don't remember which problem this was, but it's from one of the homework or some things. So we're given this function, f of x is equal to x times x minus 2 to the 1/3 power. And we're asked to find where does this function, where does f of x have horizontal tangent lines? So let me ask you all, if we're trying to find where a function has a horizontal tangent line or lines, we're really asking what?
Where is the derivative of 0?
Exactly. So we're going to take the derivative as equal to 0. Now, that's probably the more standard question. The other question that's being asked is, what about vertical tangent lines? And to answer that question, we're going to find where the derivative, well, a vertical line has what kind of slope? Undefined. So we're going to look for where the derivative is undefined. So we're going to look for f prime of x being undefined. I will point out that the original function itself is defined everywhere. X times x minus 2 to the 1/3, but you can always take a cube root of any positive or negative number. So this function has a domain that's everything. It's continuous. It might not be differentiable everywhere, but it certainly is continuous. So let's go ahead and find its derivative. So f prime of x is going to be, gotta use the product rule here. So the derivative of x is 1 times x minus 2 to the 1/3 plus x left alone, and the derivative of x minus 2 to the 1/3 is 1/3 times x minus 2 to the negative 1/3. And I'm going to think about the chain rule here, even though I don't really have to. My derivative of x minus 2 to the 1/3 is 1/3 times my stuff to the negative what? Guys, let me get away with all kinds of crimes over here. What should that power really be? Negative 2/3, right? Please don't let me get away with that. I wasn't trying to, but if you see me make a mistake, call me out. I definitely don't try to make mistakes usually, but or if I do, it's really obvious. I'm like, what did I do wrong here? Like so. If I make a mistake and I don't catch it, please let me know. And then I would think about multiplying by the derivative of the inside because of the chain rule. But in this case, that's just going to be. I'm not going to write that. All right. So, in my opinion, there's an obvious value of x that we should think about here. What is it? 2. If you plug in 2 to the derivative, what do you get? No. You get 0 here. I should say you get 0 to the 1/3 power, and the cube root of 0 is 0. Over here, you get 0 to the negative 2/3 power, which is 1 divided by 0 to the positive 2/3 power. 0 to the positive 2/3 is 0, and 1 divided by 0 is undefined. So you have to be extra careful here. So you might have mistakenly answered that 2 is where you get a horizontal tangent line, where in actuality, 2 is actually where we get a vertical tangent line, because 2 is what makes this derivative undefined. Now, that said, this isn't the moment to really start looking for those things. Although one or two of them might seem obvious, like, oh yeah, I see if I plug in 2, both these pieces kind of go away. Although again, be super careful about 0 to a negative power. Yeah, there's a couple ways to go here. I would probably try to factor out. You might try getting a common denominator if you prefer. Either way is fine. But I'm going to think about factoring out the smaller power of x minus 2. So I'm going to factor out x minus 2 to the negative 2/3. And I'm left with, here I'm left with an x minus 2 to the positive 3/3. And over here I'm left with a 1/3 x. That's the way I like to do it, but other people you might also do it like this. You might say this is equal to x minus 2 to the 1/3 plus x over 3 times x minus 2 to the positive 2/3. And then you might get a common denominator by multiplying this by x minus 2 to the 2/3 over x minus 2 to the 2/3. You essentially get to the same place. This looks still kind of gross though. I don't love this. What I might do is factor out a 1/3, which I know is maybe the more, God, I feel like I'm not saying, like, that's the way I'm thinking of it. And really, that's not the best way to say it. What we should, I think maybe getting a common denominator here is the more logical way to think about this. So you could say, cool, we have 1 over x minus 2 to the 2/3. And then inside these brackets, I have an x over 3 over here. And I guess I'd like to have 3 times x minus 2 over 3 right there, so that things can just look a little bit nicer. So then I'm going to actually now factor out the 1/3 because I can. And if I factor out the 1/3, I'm left with inside a 3 times x minus 2, which is 3x minus 6 plus x. So solving this or making it look a little bit nicer, 3x plus x is 4x. So I have a 4x minus 6 divided by x minus 2 to the 2/3 and a 3. Okay, easy question or easier question. What value of x makes this derivative undefined? What makes us divide by 0? Exactly, x equal to 2. So x equal to 2 gives us a vertical tangent. Because f prime of 2 is undefined. What value of x gives us a horizontal tangent? Or what value of x makes this whole thing equal to 0? Well, it's a little more work. If it's at the top equal to 0, it's going to be like 6 over 4, which reduces to 3 over 2. So x equals 3 over 2 gives a horizontal tangent line. Tangent does end with the letter T. And I think it's worth all your whiles to graph this on Desmos and actually take a look at it. It's kind of neat. Yeah, do we actually? Yeah. Wait. Yeah. Yes, definitely. Do you have one in mind? Those can be tricky as well.
To find the 3 halves, how did you find?
I'm setting that. So basically, I'm either setting it equal to 0 or finding where it's undefined. When you set a fraction equal to 0, we're typically just looking for where the numerator is equal to 0. So I'm really just setting 4x minus 6 equal to 0, getting 4x equal to 6, x equal to 6 over 4, which reduces to 3 over 2. So the thing when you're factoring out something, when you got something to a power, something else does another power, we can always factor out the smaller power. And when you do that, you're essentially subtracting that power from the other one. So like when I factor out the x minus 2 to the negative 2/3, well, x minus 2 to the 1/3 divided by x minus 2 to the negative 2/3 is like x minus 2 to the 1/3 minus 2/3. But 1/3 minus 2/3 is 1/3 plus 2/3, which is 3/3. Almost always what ends up happening when you do this factoring is your leftover piece has a power of 1. Let me actually, before we get to the question you have, let's look at one more example. Let's say we want to, find what I'm going to call just critical points, because that's actually what this question is finding where either the derivative is 0 or the derivative doesn't exist. Find the critical points of, I'll say something stupid, that's fine. F of x equal to x plus 3 to the 5th times x minus 2 to the negative 7th. I will point out this function is undefined at x equal to 2. So you plug in 2, you get 0 to a negative power, which is undefined. Anyways, so taking the derivative, using the product rule, it's going to be 5 times x plus 3 to the 4th times leave the other piece alone, plus switch it up, x plus 3 to the 5th times the derivative of the other piece, which is -7 times x minus 2 to the -8. And technically, I should have been thinking about the chain rule, both of those, but each chain rule would have maybe multiplied by 1 because the derivative of x plus 3 is 1 and the derivative of x minus 2 is 1. But whenever your inside stuff is more complicated than just x, we should always be at least thinking about the chain rule. Okay, and if I wanted to say find where this was equal to 0, aka find where I have a horizontal tangent line, I would do the same sort of thing where I'm factoring out the smaller, meaning less positive or more negative powers of whatever common pieces I have to each piece. So let's see, I have an x plus 3 and I have an x minus 2. I'm going to factor out the lesser power of x plus 3, which is the 4th power. I'm going to factor out the lesser power of x minus 2, which is the -8th power. But when we're factoring out, what you should really be thinking is, I'm dividing each piece by this. So, for this first piece, I'm left with a 5. I divided x plus 3 to the 4th by x plus 3 to the 4th, so there's none of them left, or there's a 1 left, if you want to say like the number 1, not like the first power. And then x minus 2 to the -7th divided by x minus 2 to the -8th. Let's see. X minus 2 to the -7th divided by x minus 2 to the -8th. What did I do with those powers? And what's -7 minus -8? +1. -7 minus -8 is -7 plus 8, which is +1. Which I will tell you from years of experience, that is almost always the power you're left with when you do this process, especially if there's a product or a quotient rule. The leftover power after you've done the factoring out is almost always a power of 1. It just is, because of the nature of how how derivatives work and how the product rule works. It's just what happens almost every time. So here you have an x minus 2 to the 1st. Same deal over here. We divided x plus 3 to the 5th by x plus 3 to the 4th, and we're left with x plus 3 to the 1. And we have a -7 as well. And you won't have any x minus 2s because they all went away. Now, what I really think about when I do this is, if I multiplied it back through, would it be right? If I multiplied this piece by the first piece, let's see. X minus 2 to the -8 times x minus 2 to the +1, you add those powers, and -8 plus 1 is -7. And if you multiply this piece by that piece, x plus 2 to the 4th times x plus 2 to the 1st, 4 plus 1 gives you a power of 5. So it checks out. And then if I was trying to solve this equal to 0, because I said we're trying to find where you have horizontal tangent lines, I would say we have x plus 3 to the 4th times x minus 2 to the -8. And simplifying the insides here, I have a 5x minus a 7x, that's a -2x. And I have a -10 minus 21, the -31. So if I'm setting this equal to 0, I see that there are 2 solutions. One of the solutions is x plus 3 equal to 0, or x equal to -3. The other solution is -2x minus 31 equal to 0, or -2x equal to +31, or x equal to -31 divided by 2. And x equal to 2 is not a solution to this question. We don't have a horizontal tangent line at 2. We don't even have anything at 2 because this function is undefined at 2. Unlike the previous example where the function was still defined there, but the derivative wasn't defined. This function has a vertical asymptote at 2. You definitely can't have a horizontal or a vertical tangent line at a vertical asymptote. So nothing is happening at 2. That's not okay. There's a vertical asymptote at 2. But like, there's no critical point. So I kind of got off on a tangent there. You had a question about, I know, I'm sorry, you gotta go for the obvious terms. You said you had a question about finding the tangent line through a curve that goes to like a point. Do you have one in mind? Totally, yeah, yeah. I also see that, I feel like I saw one on one of these webworks as well. That's kind of weird. Go ahead. X squared minus what? Okay. So like, oh, sure, yeah. So we want to find the equation of the line, or maybe lines, there might be two. Probably just one though. No. Yeah. Find tangent to f of x passing through the point was 1, -1. Okay, not that you have to draw a picture here, but I'm just going to draw a picture to help me see what's happening. So my parabola is x squared minus x. It's got intercepts at 0 and +1. It looks vaguely like this. And then I'm looking at the point 1, -1, which is down here. Maybe a little, made extra. So I'm looking for some line, and maybe I'm just going to draw it kind of guessing, kind of like that passes that point. But maybe it's actually this line. Maybe there's two lines. We'll find them, whether or not there's one or two of them. So what I want to point out is we don't know what the point of tangency is. If we did, we'd be done, right? We'd have this point and that point, we could find the slope, so on and so on and so on. So since I don't know what this point is called or what this point is, I'm going to give it a name, a variable name. For whatever reason, when people do these problems, you usually don't use X. You usually use like the letter A. I don't know why, but people do. So I'm going to call this point A comma f of A, or A comma A squared minus A. And it doesn't matter if I label this one or that one, the process is still going to be the same. So when you're doing problems like this, the general idea is find the slope in two different ways. I have 2 points. I can find the slope. So one way of finding the slope is saying, great, my slope is the difference in the y's, a squared minus a minus -1, over the difference in the x's, a minus 1. And we might simplify that, we might not. What's another way I could find the slope of the tangent line? The derivative. So the other way we're going to find the slope is it's going to be f prime at, oh, we don't know what the point is. So we're just going to say it's f prime of a. Well, the derivative is 2x minus 1. So the derivative at a is going to be 2a minus 1. And then, since these slopes have to be the same, we're going to set them equal to each other. So we're going to set, and I'm tired of this green pen here, we're going to set this a squared minus a plus 1 over a minus 1 equal to 2a minus 1. And if that numerator factored, I would factor it, but it definitely does not factor because there aren't numbers that multiply to +1 and add to -1. At least not nice integer numbers. There might be some weird irrational numbers or imaginary numbers. I'm going to multiply both sides by a minus 1. So I've got a squared minus a plus 1 equal to 2a minus 1 times a minus 1. Multiply out the right-hand side. You get 2a squared. You get -2a plus, -2a minus a, which is minus 3a. And then -1 times -1 is +1. Look, yes, the ones cancel. That's convenient. And if I bring everything to the right-hand side, I'm going to have 0 on the left. 2a squared minus a squared is a squared. -3a plus a is minus 2a. And 1 minus 1 is 0. So we can factor the right-hand side and get a times a minus 2. So it looks like we either have a equal to 0 or a equal to 2. Now we're not done, but we're most of the way there. So I'll point out, using, in my opinion, the easier of the two slope equations, if a is equal to 2, our slope is going to be f prime of 2, which will be 2 times 2 minus 1, which is 3. And then we have a slope. We have 2 points, really. You can either use this point or whatever that point happened to be. So our points are going to be either 1, -1, or if a is 2, you get 2 comma 4 minus 2. I'll point out the slope between those 2 points is positive 3. From 1, -1 to 2, 2, you go over 1 and up 3. So you could use those points and that slope to find the equation. You could say it's y minus 2 equals 3 times x minus 2, and then simplify it as y equals 3x minus 6 plus 2 is minus 4. And the other one, where a is equal to 0. If a is 0, our slope is going to be 2 times 0 minus 1, which is -1. And our points are going to be 1, -1 again, or 0, 0. I will point out again, the slope is exactly what we said it was, right? The slope is -1, and from that point to that point, you're going over 1 and down 1, the slope is -1. And then since I might as well use the easiest point here, my equation is just going to be y equal to -1 times x. So those are the two equations of lines that are tangent to the parabola that happen to go through that particular point. The key piece of information here is making sure that you recognize that you can find the slope in 2 different ways, set those equal to each other to solve for a, which gives you the point of tangency. I said the points really because there's 2 of them. Yeah.
So the reason you said or found that there's 2 lines is because you got 2 values?
Yeah.
So
Mm-hmm.
if that was linear, then there's only 1 line.
Yes, yeah, and sometimes you might get only 1 line, or sometimes you might get no lines, depending on, like, if your point was placed like here, I don't think there's any points of tangency where you draw the line through that. So certainly your number of answers depends on where the point is relative to the parabola. But if someone's asking you this question, there typically should be at least 1 answer. Yeah, that's the general idea. It's a little annoying, but after you've done it a couple times, it's not too terrible. All right, I would love to say more, but I can't because it's 2:30, so I will stop talking. Office hours as usual. Thursday, we'll talk about implicit differentiation.